Alright, so let's go in the other direction. So we're assuming that this expression is true. So this is true. So now, I'll prove it by contradiction. Assume that n is not a prime number. So n is equal to u times v, where 1 is less than u and v, and that must be less than n minus 1. If this is the case, then n minus 1 factorial is divisible by u and v. So that means that n divides into n minus 1 factorial. So if you look at the entire expression, you've got 4 times n minus 1 factorial plus n plus 4. So n divides into this, and n obviously divides into this, and you've got 4 left over. So if n does not divide into that, so n does not divide into the entire expression, and we get a contradiction. The only way this is possible is if n is equal to 4 or 2 or 1. But you can check each of these cases. So if n is equal to 4, say, you'll get n plus 2 is equal to 6, and then the expression becomes 4 times 3 factorial plus 1 plus 4, so you get 32. Right, so you've got, so 24 obviously does not, 4 times 6 does not divide into that, so we get a contradiction. In each of these cases, so for n equals 4 we get a contradiction, we'll get a contradiction for 2 and 1. So that means that n cannot be have proper divisors. So n must be prime. Similarly, if we let n plus 2 is equal to u and v, similar again, u and v in between these values, that's saying that n plus 2, so that says n plus 2 divides into n minus 1 factorial. Look at the entire expression. You've got 4 times n minus 1 factorial plus 2 plus n plus 2. So n plus 2 divides this expression, it divides this expression, and we have a remainder n plus 2. So once again, n plus 2 cannot divide into this expression. You always get this remainder. Unless n is 0, once again a contradiction. So either way, if n plus 2 or n is not a prime, we get n plus 2 or n cannot divide in the expression, and the expression cannot be equal to 0. So therefore, you've got n, and n plus 2 must be prime.